This branch of chemistry is called organic chemistry because the compounds that we'll be studying were initially found in organic matter and were derived from organic matter. We begin with crude oil. Formed by decayed organic matter under pressure over a long period of time. It is a mixture of hydrocarbons of different carbon numbers, that is, number of carbon atoms, and thus molecule lengths sizes extracted from the depths of the earth. They are called hydrocarbons because they are made up of hydrogen and carbon atoms only, and with different molecule lengths, thus sizes, their boiling points would thus be different. And that is because the intermolecular forces acting between small molecules will be lower compared to larger ones. Therefore, a lower boiling point for smaller molecules, higher boiling point for the larger molecules, and thus a trend in the boiling points with respect to molecule size can be established. This means the best separation technique for crude oil will be fractional distillation, where we take advantage of the various boiling points in the mixture in order to separate the constituents of the mixture. The fractional distillation in the case of crude oil is slightly different in its features and operation from the one that you might be familiar with in the chemistry lab. Here, the fractionating tower or column can be more than 60 meters high and has perforated trays that permit upward flow of vapor and helps in the collection of condensed constituents into what is called fractions. Each of these fractions is also a mixture, but with lower range of carbon atoms per molecule. In order to understand how we get these fractions, you need to know how the fractionating column works. The temperature at the bottom of the column is very high, while at the top it's much cooler. Therefore, a temperature gradient is being set up. That is, there is a gradual decrease in temperature from the base to the top. The temperature of the environment in the column is very high at the base, and as we go up the column, the temperature decreases. The crude oil stored in large tanks are drawn out and vaporized as much as possible in a furnace. The vaporized crude oil is then fed into the fractionating column at its base. As the crude oil vapor rises up the column, its mixtures, which are of different molecule sizes, thus different boiling points, will encounter regions of decreasing temperature. Once the temperature at that height is less than or equal to its boiling point, the hydrocarbon will condense into liquid state and is collected in its respective trays, hence fractions. The separation technique is thus based on density and boiling points. Those hydrocarbons of small molecule size, thus low density, that did not condense, that is, remain in gaseous state as a result of its boiling point being very low, will continue to rise up and be collected at the top in gaseous state. Heavy hydrocarbons of large molecule size from the crude oil that did not fully vaporize as a result of its boiling point being very high will sink and be collected at the base of the fractionating column. It is impossible to collect hydrocarbon of a specific or particular number of carbon atoms. Instead, you get hydrocarbons of a range of carbon numbers, that is, number of carbon atoms in it, which basically gives you the size of the hydrocarbon. Higher the carbon number, larger the molecule. It is very important that you understand the trend in the various properties of the various fractions that are collected as we go down the fractionating column. The smallest and simplest of the hydrocarbons has one carbon atom in each molecule and is collected at the top as gaseous state. The largest and most complex of them can have up to 100 carbon atoms per molecule and is collected at the base as waxy or semi-solid state. Therefore, as you go down the column, the number of carbon atoms per molecule increases, thus the molecule size increases, resulting in an increase in their intermolecular forces, an increase in its viscosity, hence a decrease in its flammability, therefore an increase in its boiling point. In terms of state and density, the fractions are collected in gaseous state at the top, therefore lowest density, liquid in between, increasing density, and eventually waxy and waxy solid towards the base, highest density. In terms of color, the fractions are colorless gases at the top, eventually turning more and more brownish in liquid and blackish at the base. There are names given to each of these fractions based on which part of the fractionating column the hydrocarbons are collected from. Those hydrocarbons with 1 to 4 carbon atoms are collected at the top as colorless gases, that is, they do not get condensed onto the trays and are called petroleum gases and with uses as fuel for heating at homes and stored in gas cylinders. The next fraction is petrol, and it is composed of hydrocarbons of between 5 to 10 carbon atoms. It is used as fuel in small internal combustion engines such as cars and other motor vehicles. The next fraction is naphtha, with about 7 to 14 carbon atoms, and it has its used as feedstock to the chemical industry. What that means is that it is used as a source to make other chemicals such as alkanes, which are then used in the making of plastics. Next is kerosene or paraffin, used as aviation fuel, that is in aircraft engines. Next is diesel, used as fuel in heavy vehicles such as lorries and trucks. Next, lubricants and oils applied between moving parts of machinery to reduce friction. And lastly, bitumen, a blackish waxy solid with the most number of carbon atoms used in road pavements and roofing. There are two very important points to note. Firstly, the fractions that are obtained from the fractionating distillation of crude oil fall into a family, a homologous series of hydrocarbons called alkanes. They have single bonds between carbon atoms and hydrogen atoms bonded to them. You will be studying about the other families and series in the subsequent videos. Secondly, impurities do make its way into the fractions. For example, sulfur. It is found in crude oil and ends up in some of these fractions, and when they are burnt like in petrol engines, it reacts with the oxygen in the air to form sulfur dioxide, a known pollutant that causes acid rain.